Let me move on. So I discussed a bit what is non-adiabatic responses, but now I want to switch to another topic and how we fight non-adiabaticity. Let me give you some motivation why it could be useful. I mean, of course, one of the simple motivation which was mentioned in I think Eugene's lectures, that we can adiabatically prepare states.
Can I remove this?
Yeah, thanks. And this is what's, say, routinely done in cold atoms, but it applies also to other platforms and qubits and so on. So suppose you want to prepare some complicated interacting ground state. What shall we do? Well, in usual materials, like we just couple it to some cold reservoir, refrigerator, some helium refrigerator, and wait until the system cools down. But what if we deal with isolated systems like cold atoms, or nearly isolated system? Well, there, it's kind of hard to cool down cold atoms because so cold there is nothing else. Even the universe outside is much hotter than cold atoms. So this won't work. So what we can do, we can try to use a adiabatic theorem. We can prepare a simple ground state. Like, I don't know, say, prepare very deep optical lattice. And that's what's done in this Marcus Greiner group and other groups. And make sure we put exactly one atom on each lattice site in this vibrational ground state. And after that, we slowly turn on the tunneling. And then by adiabatic theorem, if we do it very slowly, we'll prepare a ground state of, say, interacting atoms. Well, now, I guess everyone heard many times about how great quantum computers are or will be. Would be, will be. Like, we have to wait 1, 2, 3 years at most, and we will live in a paradise. But I don't want to offend anyone. But apart from all these promises, there are actually very interesting questions, like physical questions, and how usually quantum computers, at least quantum annihilus work. Quantum computers are different. So it's adiabatic quantum computers. Well, it's kind of the same principle. So suppose you want to find what's the ground state of this classical Hamiltonian, where the spins are either up and down. It's classical in the sense that this is a number. There are no matrices even. But these guys are frustrated. They can be positive, negative, and they're not necessarily connected by nearest neighbor couplings. And this is actually finding this ground state is like finding a minimum of some disordered potential, many particle potential. And this can be mapped to various problems like travel salesman and so on. Again, it's not my expertise, but it's sort of clear that minimizing this thing can have certain advantages. And these problems are known to be hard. It's really hard to find them. But then we can say, well, but we have quantum mechanics, so it's great. So we'll introduce artificial magnetic field in, say, x direction, and make it very strong initially. So if we make it very strong, then we know the ground state. It's all spins are polarized along x. We can prepare it. And then we slowly anneal, change magnetic field to 0. And then we should adiabatically connect to this ground state. We solve the problem. So, but of course, there is a caveat. And it's actually the same caveat which appears again in thermodynamics. If we discuss, for example, Carnot engines. When we discuss ideal efficiency, Carnot efficiency, there is kind of a price. And the price that most efficient engines have 0 power. Because in order to realize, strictly speaking, Carnot process, isothermal process, and this adiabatic process, remember, isothermal process in Carnot is actually adiabatic for the big system because total entropy is conserved. It's a reversible process, right? So when we couple our piston to a hot bath, when we derive Carnot efficiency, we use the fact that this is SA, this is SB, and delta SA plus delta SB is 0. So total entropy doesn't change. It's irreversible. It's adiabatic process for this plus this. But normally in real engine, you will always generate entropy. So, and then this Carnot most efficient process also has another adiabatic part, right? So, and usually we are not interested in engines which have 0 power. Same about quantum computation. Yes, we can realize a adiabatic process if we change infinitesimally slowly, but we'll have 0 computational power. It will take us forever to compute something. So we don't need these guys. So now the question is, can we speed up adiabatic processes a bit? And it turns out that at least this formalism tells you how you can do it in principle and where difficulties are. And there are many open questions. So I'm not going to tell you now whether you can solve this problem or not with some tricks. It's an open question. Most people believe not, but it's not proven at least. So, and it turns out on the level of formalism, it's really trivial. Even though it's trivial, these ideas are kind of recent. So they were first proposed by these two gentlemen. They're actually chemists. They're not physicists. Demirplack and Rice in 2003. And this was kind of like was forgotten. And then Michael Berry completely independently proposed same ideas under a different name. They called it counter-adiabatic driving. Michael Berry called it transitionless driving. And then there were many papers, like starting from, not maybe even before 2010, I should put. Chris Jerzinski, maybe many of you heard about him, was one of these pioneers. They kind of started this field, and now there are many experiments and so on. And the idea is kind of trivial. So we discussed that the moving frame Hamiltonian is this diagonal part. Now I use tilde frame to highlight that this is diagonal, and minus gauge potential. And this is fake term comes from just the fact that my basis changes in time. And this is the term which is actually a bad guy, which is responsible for all transitions, because this is diagonal. So how about that? We define counter-adiabatic Hamiltonian. I want to warn you, some people define only this part as counter-adiabatic. So if you read other papers, just be careful with notations. I don't think they're fully settled. Anyway, so let's define a Hamiltonian. This is Hamiltonian we are trying to implement, which will be h plus lambda dot times a, plus this Galilean term. Well, you see the trick. Now I'm going to the moving frame, which diagonalizes h, not the whole thing, just diagonalizes h. Then this part will become just h tilde plus lambda dot a tilde, right? But then I get additional term coming from this frame transformation. But this term is exactly the same as before, because I do exactly same frame transformation. Plus thing and minus thing cancel each other. And I see that my moving Hamiltonian is exactly diagonal. So I suppressed all the transitions, solved all the problems in the world, right? So sounds like crazy, but let me try to convince you that it's not that crazy. It's something which you know very well. It's something we do in practice very well. So let's imagine that we have a waiter who kind of tries to bring the glass, the food, from one end of the room to the other end of the room. And the goal is to be adiabatic. And that means that water should be still, or food, whatever. So waiter can just move very slowly, and obviously nothing happens, right? But if the waiter is too slow, probably he or she will be fired because it's extremely inefficient. So waiter should try to run, but then you know what can happen. But then a smart waiter will tilt the tray. It requires some skills. It's not easy. If you don't know how to do it, and I don't, then you will introduce the splashes. You won't be completely adiabatic. But if you're a skillful waiter, you will be able to do it very nicely. And then you kind of tilt more as you accelerate and so on. I'll try to convince you. This is an example of this counter-adiabatic term. So this is something which is not that crazy, even though we are using some complicated quantum formulas. It's kind of part of the motivation when I was trying to say there is nothing quantum in this term. So details could be quantum, but this is just some canonical transformation in classical system. OK, so let me go to this first simple example, and we'll immediately realize that we know what it is. So we rotate magnetic field in this xz plane. So we're changing theta. And as we discussed, generator of these rotations is sigma y. Sorry, here there is no reason for switching from tau to sigma. It's just slides compiled from different talks. So that's the only reason. So this tau is sigma. Anyway, so it's a Pauli matrix. So this is tau z, and generator is this tau y. And then, well, as a waiter, we can rotate very slowly, and then this is not important, and we follow the ground state. Or what we can do, we can compensate counter field. Oh, now I remember why I called it tau. Because this is moving frame, in this tau z in the moving basis, and this is sigma in the lab basis. But anyway, so the sigma y is this Pauli matrix along y in the lab frame, so we don't need to think about anything. So that's what we are implementing. And of course, you know very well why I'm doing it. Because if I'm rotating magnetic field, I can go to the rotating frame. But because I'm going to the rotating frame, there is an extra, this angular momentum thing. There is magnetic field along y. And I'm introducing real field along y, which kills exactly this fake field. And now in the rotating frame, there is nothing. And if there is nothing, there are no transitions. And yeah, this I will discuss later. And moreover, you can take the limit when you rotate very, very fast. And then the Hamiltonian becomes irrelevant. And this kind of motivates why I was choosing always minus sign in this gauge potential. So let me just explain it a little bit more slowly. So let me take the limit when theta dot goes to infinity. So it's effectively my Schrödinger equation, which I'm solving, or which I'm implementing in the lab, is this, right? Times psi. And this my H is this spin in magnetic field. Everything in the lab frame, so it's basically rotating magnetic field. But now let me rotate faster, 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 and faster. Well, you see this becomes less and less and less and less important. So when you rotate very fast, we can forget about this, right? So it's only this term with plus sign now, right? Now minus converted to plus, it's counter-adiabatic, which does the job. Moreover, I can see that, well, this becomes very big. There is no free lunch. If you want to do something quickly, you have to introduce some large term in quantum mechanics, this energy time uncertainty if you want. But now it's convenient to change variables. I will say that, well, I have a single variable theta. Think about this as a proper time if you want. I can define d by dt of psi is d by d theta of psi times theta dot. And I can write it h bar sigma y theta dot times psi in this limit. Theta cancels, so there is nothing large anymore. And I see, and this is, of course, completely general. So I see that, indeed, this counter-adiabatic driving in the very fast speed, just a second, reduces to implementing gauge potential as a Hamiltonian. So if you want, this gauge potential is the Hamiltonian which does adiabatic transformations for you with plus sign. So you just apply it in the lab, and it does the job. Just one more thing, and take your question. And here we know why this works, right? So we are trying to rotate spin from, say, x to z direction, or z to x. So what I'm telling you is that, well, instead you can just apply y magnetic field and wait. It's kind of obvious. But this is a limiting case of this counter-adiabatic driving. And that's what it's a bit surprising why it took so long for people to sort of realize how it works in general. Yeah?
Maybe I got it wrong, but do we actually add this CD term just in order for it later to cancel?
Yeah.
So it's actually...
But in a lab, we do add it. So physically, we add it. So it's canceled in this fake frame moving, or I don't know whether it's fake or not fake. So in the moving frame, it's canceled.
So can we just say that we renormalize our Hamiltonian?
I don't know in what sense it's a normalization. We just add another term. I mean, this term is different.
Well, it's actually the counter term. The counter term to our well, to our bad term, which
yes.
cannot allow us to.
Yes, but usually by renormalization, people mean like quite specific things.
Well,
I don't know.
Renormalization,
It's just rescaling of parameters. So.
And here we avoid non-adiabaticity.
Well, usually renormalization is kind of rescaling transformations, and here it's not rescaling, it's addition. But I mean, you can call it whatever you like. It's not important. But you're just basically adding in the lab this counter term. Yeah, if you want to call it renormalized, I don't object.
Can I ask that?
Yeah.
Do I understand correctly that after this counter-adiabatic term was added, the state of the system follows the ground state of the eigenstate of the original?
Yeah, exactly, right? Exactly, at all times. Yeah, and this is really important because you're getting, when I'm showing waiter example, waiter is not doing that. Because ground state of original Hamiltonian is a steel glass with zero momentum and no tilt, right? So it turns out waiter is doing something else. It's now known as fast forward driving, but let me show it in the next slide. So yeah, and this is the example. It's a simplified waiter. It's a particle in the box. So the waiter tilts the tray to introduce gravitational field. So I can, yeah, let me do it through a simple example. It's very instructive. So we do particle in the box, and now we want to move a box. And as I discussed before, if we move box slowly, we just get some extra mass and so on. Probably not a big deal. But if we move box fast, we just excite this particle. It will be irreversible. Once you excite it, you cannot de-excite it, unless you really fine-tune. But you need to know all the phases. It's very difficult. So it's against thermodynamics, even for one particle rules. So in order to move the box from this position to this position without exciting this particle, again, what I can do, I can move the box slowly. Or I can recall that my moving frame Hamiltonian get this Galilean term, and we can just compensate it. So we can just add this Galilean term back. And then a particle in a box will follow exact ground state. Well, it's hard to get this. It's hard to add this term, unless particle is charged. And anyway, so when waiter is moving water, you cannot get. So this linear momentum term, it's something which doesn't happen. But now we know, of course, something from electromagnetism, that we can shift the momentum. And when we shift, well, this is just a constant. X naught is my external parameter, so I can sort of ignore it. I shift the momentum. And then I can do this transformation. P goes to P minus mx naught. So I can do the standard tricks. And then what I introduce is a counter-gravitational field. I think actually there should be minus sign, but before should be plus. Anyway, you understand what was going on. So this counter-adiabatic driving, after this extra shift, reduces to what we know very well. If I want to move elevator very fast, effectively in this elevator, this box, I create very strong gravitational field, which will excite my particle. So in order to avoid it, I introduce gravitational field with opposite sign, and then I have a free lunge. So particle in this accelerated elevator is not excited. It doesn't feel any forces. So this counter-adiabatic driving kind of makes sense. But then there is one subtlety that by doing that, we actually follow not a ground state of original Hamiltonian, but of shifted Hamiltonian. Or if you want, it's our shifted momentum which doesn't change, right? Because our original momentum is shifted by mx naught. So in the quantum language, what really we do extra unitary transformation. And actually, we follow a ground state of h prime, not h, but h prime, where h prime is rotated by u. But as long as my unitary, and this is my unitary, right, because that's what shifts the momentum. But as long as my unitary is zero in the beginning, identity in the beginning and identity in the end, it doesn't matter. Because I end up in the same ground state. So I found another path in my space. So another Hamiltonian. so Hamiltonian H prime, not H. And I'm saying I will instead follow ground state of Hamiltonian H prime. But as I said, in the beginning, in the end, it coincides. And that's a mathematical reason why waiter, when waiter stops, it tilts back. So this, he recovers the ground state of original Hamiltonian. It's kind of a subtlety, but it's really important. Because in this way, when we introduce this, what's known as fast-forward driving, we do not follow instantaneous ground state of H. We follow instantaneous ground state of equivalent H. And that's actually where many difficulties are, how you find good equivalent H, which ground state you want to follow. So now we can do the same example with dilations. And again, I kind of understand that you probably don't have time during the school. But if you are interested, I urge you to go through this exercise because it's interesting. You can get some insights. Anyway, so let me just first highlight what's going on, and then I'll tell you which insights you can get. So we discussed that if you move one wall, then our effective Galilean term contains dilation operator, so my counter term should also contain dilation operator. That means this is what I should implement, right? But again, I can do the same trick and fast-forward Hamiltonian. You just add a bunch of terms, you just do the algebra, and you get this. So you introduce extra harmonic potential. It's basically the same as we discussed in the moving frame, except the sign is opposite, right? In counter-adiabatic, I have plus sign. When we go into a moving frame, you're getting minus sign. Anyway, so it's harmonic potential proportional to acceleration. And this first was derived by this guy's gentleman, Defner, Gerzinski, Del Campo. But then it turns out there is an interesting exercise that you can just write Hamiltonian equations of motion for rescaled variables. P times lambda is L, and x over L. And actually what you will find that these rescaled variables actually don't know anything about your L. It drops out completely if you simultaneously rescale time. So far I was not touching time. It's kind of like, cannot touch it. No, you can. And this kind of extends the notion of canonical transformations and so on. And then it turns out that if you're accelerating too fast, you can get things like horizons and so on, because time in the moving frame can be finite, while time in the line frame is infinite. So you can get all these things which you discussed in terms of black holes and so on in this simple example. And physically, it's kind of clear that if you move very fast, this particle will never catch the wall. So it cannot be that this static problem works for infinite time. So I think you can get, at least if you are interested in this, you can probably learn many insights from this exercise. OK, so now I'm going to the equation which I wrote early on. And now we deal, say, with moving to closed systems. And for various reasons, either counter-adiabatic driving or like understanding, say, mass correction or other reasons which I kind of mentioned, dressing the eigenstates and so on, we want to know what this gauge potential is. So we need to know how to solve this equation. And I already mentioned, remember, this formal solution. It's here. But as I was arguing, this formal solution is useless because you cannot really translate it. But now, using the notion of metric, which is essentially norm of gauge potential, we can even find that this not just useless, but essentially this guy doesn't exist as a local operator. How do I see it? Well, I can compute, they should be connected things here anyway, it doesn't matter. I can compute norm of this gauge potential, which is variance, and this is the same as the metric tensor, distance between wave functions as we discussed, right? It basically defines how big this term is. And normally, if we talk about, say, spin systems, right? When we talk about Hamiltonians, they should be extensive in number of degrees of freedom, right? Maybe non-extensive if I have just some local thing. But usually we deal with some extensive forces, and everything is extensive. So what about this guy? Well, there is a formula. If I know this formal solution, I can plug it in. And then I find that this norm of this gauge potential, the metric tensor, is the sum of this matrix element squared over energy denominator squared. But this is in particular, it's a kind of a trivial statement larger than one of these terms, right? Sum is always larger than 1. But now I can use some facts, or these are not facts, these are kind of, again, hypotheses which are very recent, and, but which were numerically confirmed, which make sense, and no one, I think, doubts them. So you'll hear probably much more about this from Dima Abanyan lectures. It's that in chaotic systems, essentially there are no selection rules between matrix elements. And a refined version of this statement is known as eigenstate normalization hypothesis. I'm now talking about generic chaotic systems. There are integrable systems, so on, exceptions, as I'll discuss later. And there, just from simple normalization conditions, you can just show that off-diagonal matrix elements scale as e to the minus entropy over 2. And energy difference between nearby states scales as e to the minus s. I mean, essentially, this is really a trivial result. So if I compute average of some operator, say magnetization squared, well, it's again connected. This should be finite. Maybe it's extensive, but it shouldn't be large. But this I can always write as sum over m not equal to n. I'm computing average in some eigenstate n. Doesn't matter. This is sum of n a m squared, right? There are no selection rules, so it means all of them are roughly the same. But what's the number of this? It's given by density of states. Density of states is e power entropy by definition. So it means that this guy should be compensated by e power entropy. So each of them should be e to the minus entropy over 2. So just the fact that you have no selection rules alone tells you that this has to be the case. But of course, there are some refinements and so on. But anyway, so if we stare at this, we have e to the minus s in numerator, e to the minus 2s in denominator at least, and we have more terms. And we see that this norm of this a grows not linearly, but exponentially in system size. It actually means there is no local operator which can possibly satisfy that. So I just proved to you that trying to solve this equation, at least exactly, is totally useless in generic systems. Situation is different for the ground state. For the ground state, I don't have this. I have a gap, and there is nothing exponentially big here. So everything is well defined. But once I go to excited states, this becomes difficult. So now we have to abandon idea of trying to solve this equation from the very beginning. We just shouldn't even try to solve it, because we know there is no solution. So what shall we do? Well, and here there are kind of two approaches, at least two approaches I can think of. Is first, try to find classes of Hamiltonians for which solutions are possible. And this defines connections with integrability. I'm not really expert there, but there is one example which I'll walk through together, with you, which kind of shows very interesting connections between quantum and classical integrability. As far as I understand, it's very generic, and as far as I understand, it's very unexplored. So it's not that this equation is not known, but as far as I understand, like all these implications which we were discussing are not really discussed. So anyway, I'll talk more about this. Or another possibility is that we are saying, well, we cannot really choose Hamiltonian. Hamiltonian, it is what it is. But then we can try to find approximate solutions. And there is another very interesting direction with very interesting insights. OK, so let me go through this exercise. It's sufficiently simple, so I'll walk through it on the blackboard. So how much time do I have before break? Like,
about 15 minutes.
Oh, that's enough, yeah. So, and let me start from classical equations. I'll introduce quantum a bit later. So, essentially, the question, again, I'm asking, I know nothing about integrability. The only reason I use this word is that I showed you that if the system is non-integrable, then I know that there is no solution. Therefore, if there is a solution, the system has to be integrable. But I don't know, I'm not going to use anything like inverse scattering method or whatever, which I don't know what it is, or Berti ansatz or whatever. I'm just trying to solve this equation. So d lambda h minus A lambda H. And this should commute with H. So the simple thing is to say this is some function of H. I'm not pretending that I'm finding most general and unique solutions. I'm just trying to find cases when I can solve it. How about starting from something simple? H will be p squared over 2m plus v, which depends on my q or x and parameter lambda in some way. It turns out that even here in 1D there is no chaos, but it turns out that still, if I require a closed form solution for this, already, as we'll see, we have a lot of constraints. OK. So, well, here, what is f of h? Well, again, I can write it c1 plus c2h plus c3h squared, perhaps. I just do this expansion. So what is A? Well, you can combine insights from quantum and classical physics. So quantum mechanically, remember, it's I over h bar commutator of A plus A and H. This is real. This also has to be real because this is real. So it means that A has to be imaginary. Because A has to be imaginary, A should be odd power of momentum. Once I know it, I can forget about quantum mechanics and say, well, a good ansatz for A will be P times some function of Q and lambda plus P cube, well, let me put 3, some zeta, which also can be function of lambda, and so on. So I know that this is, I can find solutions like this, right? This is imaginary. And I'm assuming that I can do polynomial. Again, I'm not saying that there are no non-polynomial solutions, but this is, in a way, polynomial is equivalent to locality. In quantum language, I'm local in derivatives. I don't have high-order derivatives, right? OK. So let's first start from this simplest example, just linear in P. And let's see what we can get. So I have d lambda v, right, minus dA dP dH dQ plus dA dQ dH dP is equal to C1 plus C2H. And that's enough, because H squared will contain P power of 4, and there is no P power of 4 here. So I know that all other constants have to be 0. So it's like d lambda v minus, let's see, I get f from dA dP times dQv, right? And from here, I will get P squared over m, right? dH dP is P over m. dA dQ will be P times f prime dQf, right? Is equal to C1 plus C2 times whatever P squared over 2m plus V plus. OK, so it's very simple. Now I see where consistency conditions come from. If I want to stop at this order, I want terms in P squared to match and terms at P power 0 to match. So I have to kind of satisfy both. And if I want P squared to match, I immediately see that my f is constrained, right? Because here I have a constant, right? I have h power 0 plus h power 1 times some constant, so on. Because otherwise, if it's not constant, I won't get vanishing Poisson bracket. So what it means about f? So what is the most general solution for this equation?
CQ. Plus constant.
Yes, so let me use it, AQ plus B. How do we well, now from the second equation, I will get solution for V. So, but before this, so what is this? So recall my gauge potential is P times F. So what's the meaning of A? What's the meaning of B? Remember, A is generator of my transformations. If I have only B, my A is equal to P. It's a generator of translations. If I have A, my A is Q times P. It's a generator of dilations. It actually means I can get translations, dilations, and that's it within this order. I'm done. So I gave you 2 examples. What I didn't tell you that I exhaust a family of all simple examples. There is nothing else. And the remaining conditions, if you solve these equations for V, you'll see that V should exactly satisfy the scale invariant conditions. 1 over A squared, V of Q minus B over A. And this V naught is arbitrary function. So if you solve equation for V, you will get that this is the solution. OK, so I didn't get anything new. And I even don't have connection to integrability. This is what, by the way, Yerzynsky and others called scale invariant driving. So let me try to make it more interesting. And I will get now P cube times zeta. But now I still don't want to have terms of the order of P power 4. This I can get in the next order. But for now, I want to stay P squared. And then I see that the zeta should be independent of Q. Why? Well, because if I differentiate this dA dQ times dH dP, if zeta will depend on Q, I will generate P power 4. Right? dA dQ will be P cube, dH dP, another P, it's P power 4. I can do it, but then I have to introduce here H squared and so on. But I want to do it order by order. I want to say, let me make this is Q independent. Then I won't generate P power 4. Then I can stop at this order. But then let's see what I need to modify. So I will get just additional term coming from dA dP times dH dQ. So I will get somewhere here minus zeta P squared, right, times dQV. Right. There will be additional term here. I will still get my scale invariant solutions, but now I'm getting a new solution. So you see, which comes from P squared over M dQF is equal to zeta P squared dQV. So from here, I see that F is roughly equal to V is a possible solution. I'm kind of sending all constants to 0 because they will add translations and dilations on top of this. And if F is equal to V, then I get an interesting equation. So I get d lambda V minus V dQV is equal to 0. And this is nothing but dispersionless KdV equation. So you see, I just did a trivial exercise. I just asked, can I go to this ansatz and make sure I can solve these 2 equations? And I got KdV. That's a dispersionless. And dispersionless is actually bad. It has like this shock waves on what's singular and so on. So where dispersion comes from? It's interestingly, it comes from quantum mechanics. I can now do exactly the same thing. But now I will put commutator here. And in principle, I could evaluate this commutator order by order, and it will take me some time. But there is a very nice trick, which I would explain in much more detail if I would choose a different topic for this class. And let me just say it. So this trick is known as Wigner-Weil quantization. Probably many of you never heard about this, but it's extremely usual too. It's if you want quantum mechanics in phase space. No wave functions. Now you deal with normal canonical variables. And there the key, one of the key results, is that this commutator becomes exactly, not approximately, exactly equal to a Moyle bracket, which is nothing but sine of the Poisson bracket. If you did not see it, sorry, there is H bar over 2. So what this expression means really, Poisson bracket is like skew derivative left with respect to q, right with respect to p, minus opposite. So sine will contain this q derivative, that's cube of this derivative, and so on. So in particular, in the leading order, I can say that Poisson commutator is equal to Poisson bracket. And then minus, I think I will get h bar squared over 24. I will get, remember, expansion of sine. I will get 1 over 3 factorial. And then I get square of this, so cube of this. But there is another 2. Anyway, and then I will get cube of Poisson bracket. And the reason I'm telling you is it is in my own experience, it's much easier once you know it to evaluate commutators. Then you start doing the standard tricks. Because now I can immediately say that the extra term in the commutator will be third derivative of a with respect to p times third derivative of h with respect to q. And third derivative will only act on this guy, because it's p cube. And it will give me essentially zeta. And third derivative of q will give me third derivative of v. I will add it here. And by magic, you will recover that there is an additional term, which is h bar squared over, say, 24. There could be some other factors. d3v dq cube is equal to 0. And it's interesting. This is full classical KdV equation. So it's kind of interesting. I'm asking, can I really find quantum Hamiltonian, which I can transform adiabatically without exciting the states? We are local gauge potential. My Hamiltonian is local. And from this, just asking this question, I immediately recover classical integrability. I recover classical KdV equation. This is the only example I looked at, and it turns out that it was just a year before, as it usually happens, discussed in a paper by 2 Japanese gentlemen, Takashi and Okuyama. So, but in any case, it was revealing. And mathematically, I talked to people, in particular Sasha Abanov from Stony Brook, who's really expert in this. So just understand me correctly. In terms of mathematics, I'm not introducing anything what is not known to quantum integrability community. So these equations are known under different names and so on. But the connection with this adiabaticity and so on, as far as I understand, is new. And moreover, it looks like you can get new insights. You can go to many body systems. You can try to go to disordered systems and so on. So you can really, if you try to play with it, you can construct many non-trivial quantum integrable models just by trying to find consistent solutions. OK, so this is, OK, I got signs wrong, but this is sort of the correct answer, what you'll get. So in some sense, quantum solvability and quantum integrability come together. And now what it really means physically. Well, physically, it means the following. So I'm trying to have a particle in some potential. And this potential should satisfy KdV equation. And KdV equation has solitons. Right? I probably don't have animation here. Oh, no, it is. OK. So this is a fake motion of but the fake, in a sense, it's a motion of a classical soliton. And then what I'm saying that if I define a potential which has this shape and which moves in this way, then I can design a Hamiltonian such that I will not excite a single particle outside. This is a kind of dynamical integrability. If you think about this, it's amazing. Even if you take most integrable non-interacting model and you start to push some obstacle, you'll excite lots of particles. Here I'm saying you can avoid it. Moreover, you can do it even in this 2-soliton solution, which looks even less trivial. So you know bigger solitons move faster. So you can realize sort of this, think about this as tweezers. You can move these tweezers through each other, and nothing will happen. But if you do it naively, you will still excite particles. So what you should do, you have to realize counter-adiabatic Hamiltonian. And counter-adiabatic Hamiltonian has plus lambda dot times the gauge potential. Gauge potential is negative, so it's a minus. But anyway, so you have to realize this Hamiltonian with p cube. So that's where and that's probably where our intuition fails, at least my intuition fails. Because I understand that if I move the object, I will excite particles. Well, just from kinematics, particles collide, they disperse. But when you say, but I introduce Hamiltonian which contains p cube, I just don't know what's going on. I have no intuition. I never tried to solve this problem. I know from formally that if I realize this Hamiltonian, and this, by the way, for experts is called, I think, second Lax operator. Maybe this is probably first. Nth, maybe it's second, maybe it's third. Anyway, one of the lowest Lax operators. So if you realize this Hamiltonian, then you will not excite anything. So one can ask, like, how you can do it. And here, this is work in progress. But again, I finished our paper. And of course, like months ago, there is another pair. Here, Floquet helps. It turns out, I don't know about this particular one, but it turns out that in many cases, you can do Floquet engineering. And it's not a coincidence. You can actually fight dissipation by doing Floquet. If you shake in the right way, you can generate these terms effectively, and then you suppress dissipation. So, and this is like really open field. So, well, now let's move closer to situations when we don't want to engineer Hamiltonian, but when we already have Hamiltonian, and we want to solve this equation. So this is a particle in electric field, and let me make long story short. Well, gauge potential, it's not interacting still, but already many particle. So in some potential. So gauge potential is still imaginary. It's not interacting, so it should be just hopping if you think about it. Because if it's imaginary, then it should be like a current, right? But it could be non-local current. Anyway, it's most generic solution. And it turns out that if you have a linear potential, that's another example when you have exact electric field. Let me skip all the complicated formulas. You can, I'll mention this a bit later. I'll just show you a picture. So you want to turn on electric field, say, adiabatically, without exciting particles. And that's difficult. You have to turn it very, very slowly, right? If you turn electric field, particle starts to move. How you can turn electric field without exciting them? And it turns out if you will go through this machinery, you'll get, it's kind of another way to problem if you want, but it's more subtle. At least I don't have much intuition to say why the solution is like this. So instead of this red line, this is a naive line. You turn electric field from some small positive value. If it's 0, you start getting various singularities. So even with counter-adiabatic driving, it becomes non-local and so on. But if you start from a very small but finite electric field, and you turn it to a large value, then of course you can try to do it like slowly. It's some random, like you can try a linear protocol and so on. It's kind of nice to be good and smooth in the boundaries. But it turns out that what you can do instead, and realize essentially 100% fidelity, is that you apply extremely strong magnetic field in the beginning, electric field, sorry. Then you make it so you can accelerate particles very fast, and then you catch them. But if you think about this, that's exactly what you want to do if you want to tilt bucket of water. Of course, you can do it slowly, or you can just over-tilt it, and water moves right, and then you catch it. If you're skillful, you will do it. So this type of solutions actually reproduce this logic, but of course, these details are kind of probably hard to guess unless you're really experienced. So if you experience water catcher in the bucket, you will probably know this protocol very well by heart. I don't know.
Can I have a question?
Yeah.
Adiabatic driving is rather robust, so you can drive it this way or that way. If it is slow, then you get to the final state, right? Is this protocol robust? So if you have a tiny error in your protocol, will this blow up even higher?
No, but you see, yeah, this is an interesting question. That's, of course, related to locality, because as I said, you evolve with your gauge potential. But this is, if gauge potential is local, then you evolve with normal Hamiltonian. And you ask, how robust you with respect to normal Hamiltonian driving? And normally, if you have a local Hamiltonian, you are kind of robust, right? If you do a quench or some protocol, if you do small mistakes, you don't, small errors in the protocol, don't introduce large mistakes, unless you say cross a critical point, unless something happens. But or if your Hamiltonian is this gauge potential is less local, so it's more fine-tuning, then you are less robust. But So I think at the end, robustness is also related to this metric tensor over gauge potential. But this is not the question anyone I know studied really in detail. So, but well, you see numerically at least that locality enforces robustness. And moreover, now for this two-level system, there is experiment in Alex Sushkov's lab, in my colleague in BU. And well, they realized this counter-adiabatic using Floki. It's something I didn't really discuss. But they see experimentally that these things are extremely robust if you do Floki. If you don't do Floki, if you try to be adiabatic, they're actually less robust. And the reason is the following. So it's kind of opposite to what you say. Suppose you do a slow process. But experimentally, robustness is not determined by, I don't know, some small changes in the Hamiltonian. It's determined by extra noise. If you do things slowly, there's a lot of noise during this process. And actually, things deteriorate very fast. So that's why D-wave machine doesn't work. You cannot really be that slow that noise is unimportant. Or at least it doesn't work as it's supposed to work. So it's not really quantum annular. It's a mixture of quantum and classical. But if you would do a process fast, then you are much less susceptible to external noise. You're much more isolated. So in this sense, you're more robust. So you have to really define what you mean by robustness. But it's still an open question. OK, so now this last maybe piece of information, or at least technical information, that what if you cannot really solve this exactly? Well, and it turns out that this equation which I wrote is identical to Euler-Lagrange equations for minimization. So we can define formally this object G, which is like d lambda h. I call it x. This is an operator. And the idea that I want to find x, which is equal to a. But now I define this G of x. I drop all factors of h bar, just to save time. It's derivative of h plus I x over h. And then I can define norm of d is trace of g squared. And now, actually, without any proof, I know that minimum of d solved this. And it's actually really trivial to see. You don't need to write any Euler or Lagrange equations or anything. If I take eigenstates, expectation value of eigenstates of h of g, I'll get d lambda h plus I a commutator h. Then I will get just d lambda h. Expectation value of commutator of h, sorry, it should be x. Of commutator of h with any operator is 0 in eigenstate, right? Because h acting on here gives me a number, h acting on left gives me exactly the same number, and they cancel. So it means that whatever x I choose, my diagonal elements of this matrix are not affected. But if I choose x, which is equal to a, then all of diagonal elements are equal to 0, because it has to commute with h, right? If I have one diagonal matrix and another matrix which commutes with it, it's also diagonal. So I proved to you. So of course, trace of g squared is sum of diagonal squared plus off diagonal squared. If I minimize all of diagonal to 0, I have a minimum of this. So it's a trivial statement, but we can now explore this statement, because if you have minimization principle, we can find variational solution. Or maybe you can use perturbation theory. And this is the a scheme to build approximate, if you want, approximate connections. If you talk about mathematical language, this is like connection, a adiabatic connection, and we are trying to build approximate variational connections. So, and it turns out that mathematically this problem is closely related to many other problems people are interested in. So, like really, there is a push of finding slowest operators, and it turns out that problem of finding a slowest operator, basically operator which doesn't decay in time as long as is possible, is mathematically can be shown to minimizing trace of this commutator of this operator and h squared. So here there is extra term, but it's very similar. And, and it's related to many other problems as well. So I just flashed some answers. I know it's already late, and it's hopeless to go through calculations anyway. But let me just say that actually, as in normal quantum mechanics, this is with normal variational principle. This operator variational principle is also simple because minimizing something like a local operator is a simple problem. Solving equation is a much harder problem. Solving Schrodinger equation is hard. Minimizing expectation value of energy is easy. So it's exactly the same story here. So for example, if we have, this is the non-interacting example. Interacting, I'm not going to write formulas. You can do it numerically. So we know that my gauge potential, as I said, it's imaginary, and it contains all possible currents. But now I will use variational approximate gauge potential, which only contains nearest neighbor currents. For constant potential electric field, it was exact solution. Now it's approximate. I want to find best local currents, if you want, which minimize my effects of non-adiabaticity. So I need to find G. And as I said, you don't really need to look in these formulas. Let me just explain what I'm doing. I'm differentiating H with respect to lambda, and that's this guy. That's easy. And then I need to compute commutator of this and this. And it's also easy. Right. Now I need to compute norm of this, trace norm, so the square of this. But all these operators are orthogonal. It's like Pauli matrices. So trace of sigma z squared is 1, trace of sigma z on one side times sigma z on another side is 0. They're all traceless. So calculating norm of this guy is just squaring these coefficients. It's as easy as this. So I get quadratic minimization problem. And if I minimize it, I will get this Laplace type equation. So that's the approximate. So, and that's really easy to solve numerically or analytically continuum. So let me just show results. The result which I want to show is related again to Eugene talk. We are going now to fight Anderson orthogonality catastrophe. So Eugene said how hard it is. So you introduce a tiny perturbation in your Fermi sea, you create orthogonal state. Now I want to mimic this guy. I stole it from the web. I don't know, it's some bird. And so now I imagine I have a quantum bird. So I have my Fermi sea. Doesn't have to be in the ground state. Could be in highly excited state. And we were discussing before moving an obstacle. Now I want to insert an obstacle. But I want to remain adiabatic. Well, now because of Anderson orthogonality catastrophe, inserting slowly is almost hopeless. You have to do it slowly with rate which becomes 0 is some power of the system size, inverse power of the system size. So doing exact counter-adiabatic potential is hopeless. You have to introduce all non-local currents. It's difficult, especially in continuum. It's like crazy Hamiltonian, which contains all orders of derivatives, all orders of momentum. So how about that? Well, we put it on the lattice because it's easier. We can take continuum limit later. And we will apply this local counter-adiabatic. And these A's are just solutions of this equation, which I'll show in a second. So here my lambda is a magnitude of the potential. So if I write this equation, which I wrote before, it's this. So I can just solve it. And this is the solution. So I take specific potential. It turns out to be integral, but we didn't think about it. I don't think it's important. It's a potential. Then this is the solution of that equation which I showed. So this is the solution of currents which I have to introduce. And actually, you just see it's kind of an interesting. It's a linear thing. It's a green function of Laplace equation. It's a linear function. It has to be the case. Then it changes sign and so on. And then before I show you the results, let me say this word. So I said it's local. It's local in the sense that my currents are local, but they're long range. Even though I'm inserting impurity in the middle, I have to do long range perturbation. And this has to be the case because Anderson orthogonality catastrophe is related to the fact that I perturb my particles very, very far away. So it's really orthogonality comes from non-locality. So it means I have to push my particles very, very far away. But I can do it where this kind of shape. A question of robustness is great. We didn't study it here. So, and then we can do this Peierls transformation. It's sort of exactly the same trick with the weight. I shift momentum and so on. I don't really want to go into this. You can convert it to just changing effective tunneling and effective potential. So like with the waiter. OK, so let me show the pictures. So if I do this Waiter trick, so we'll introduce fast-forward protocol, then my potential profile will be kind of, again, has this funny thing. I want to insert impurity, but initially I actually do an opposite. So I introduce attractive potential in the middle, long range. So I want to push particles away, but the way to do it is to first push them to the middle. Then I introduce my original potential, and then I introduce stronger than original potential, push them back. So, and then I have to do also with the current, so it's kind of, so with hopping, I introduce a minimum, but here numbers are very small. Some particular reasonable choice of time, it's 100, 102. So essentially, you don't need to touch tunneling. It's only potential. And then let's see what happens. So, and this is the probability of finding exact ground state. Just want to highlight, it's a many-body ground state. So in this simulation, 512 particle. So what's the chances that I insert impurity and I have my particle, sorry, my system of particles in exact many-body ground state? If I just do simple, this adiabatic protocol, at time which is 10, everything is of the order of 1. So it's relatively slow time, but not like 1 over L squared. Then what you will get is fidelity 10 to the minus 30. And this is your Anderson-Orthogonality catastrophe. The chances that you find exact ground state are exactly equal to 0. But now you introduce this non-local current, which I first showed, and then you get this. You see, it's not exact. You don't have fidelity 1. Have fidelity 0.5. So improved by 30 orders of magnitude. So at least in this idealized world, with probability 1/2, you find exact ground state. And then if you do this fast-forward protocol, you don't follow exact ground state, so fidelity drops, but you recover it in the same value of 0.5. And it's interesting, there was a recent series of work in Innsbruck. They kind of expanded these ideas to spin systems. They realized approximate protocol for one particular glassy problem, and they found very, very good results. So I asked them whether they think they're solving NP-hard problem. They were not sure, but at least they got orders of magnitude improvement from this variational problem. Solution for actually a very difficult problem. Yeah, you can do the same tricks with moving, but let me maybe skip this. I'll try to discuss 2 more points. One will be sort of very quick, and this is also, I think, a cute direction of research, and this is related to speed limits somehow, how this machinery. So I'm going back to this, my moving frame Hamiltonian. No counter-adiabatic now. Just moving frame Hamiltonian. And then I can, well, Alexei asked about fluctuation dissipation theorem. Here it shows up. So instead of computing correction to the energy, I can compute correction to the energy variance. And then it's exactly the same calculation as we did in the very beginning, but you have energy denominator squared because it's energy. And then if you look carefully, it's now exactly equal to velocity squared times gauge potential. Norm of gauge potential, metric tensor. So we see that energy variance in the leading order of adiabatic perturbation theory is always proportional, not just in high temperatures, always proportional to the metric tensor. And then actually this fact that mass is geometric is precisely this fluctuation dissipation theory. Why I'm telling this? Well, there is an interesting, I never talked about time really, but one can formally define metric with respect to time. Why not? How fast my wave function changes in time. Well, I do. I forgot connected sign, but I do exactly the same thing. It's an overlap of time derivatives of psi. And I see, well, this is now exactly energy variance. So time metric is the energy variance. But we just proved that in the slow limit, energy variance is velocity times space metric. It's kind of interesting that close to adiabatic limit, all dynamics lives on a light cone. Well, maybe this is not speed of light, but this is how my parameter changes. But what you can also, yeah, and actually it's true either close to adiabatic limit, or it's true for all counter-adiabatic protocols. It's kind of an interesting observation. But you can show that if you go to next order of perturbation theory, then this difference is positive. So GTT is always then lambda dot squared G lambda lambda. Why I'm telling this? Well, here's the relation to speed limits. Let's just conjecture And we checked this numerically conjecture in all possible examples we could imagine. It always works, but we couldn't really prove it, except at close to adiabatic limit. Let's conjecture it's also always true that time length, which is square root of gtt over t, is bigger than space length, which is this. It just follows from this inequality, which we extended to all velocities at will. And then, well, if we now recall that this GTT is energy variance and use Cauchy-Schwarz inequality, right? So LT squared will be less than integral over time. That's integral of the square of this, which is GTT anyway. So we'll see that LT squared is less than T squared times average energy variance. I understand you probably don't follow me. But if you combine these two, you'll find something physical. You'll see that the protocol time is suddenly bigger than this my geodesic length, or the space length defined by ground state manifold, over average energy variance. And this is an interesting result. This is your speed limit. It actually tells you that physical time to reach the final state is limited by this equilibrium length. And in particular, I argued that for excited eigenstates, this is exponentially big in system size. So it actually means that if you want to prepare exactly excited eigenstate, you need exponentially a long time, no matter what. So this puts extremely strong constraints on how fast you can do it. And it turns out in simple limit, this you can prove rigorously, and this is related to Mandelstam time bound and so on and so forth. But let me actually finish with another work which is in progress by Shosigura and Anatoli Polkovnikov. I'll only show pictures here, no formulas, which I think is very cute. At least I'm very excited about this. So we can connect these local gauge potentials and emergent approximate integrability, emergent conservation laws. And let's imagine that we have this generic, well, some Ising chain in longitudinal field. I'm sure Dima will discuss much more this type of models with disorder. And it turns out that without disorder, it's like now a standard example of quantum chaotic ergodic system. It satisfies eigenstate summarization hypothesis, has random matrix structure, and so on and so forth. So, and now we can think about our parameter space as Hx and Hz. And then this model has two trivial integrable models. So one when Hz equals to 0. And this is our transverse tilde-Ising model, which I discussed, remember, when we discussed geometry. When gamma is equal to 1, it reduces to it. It maps to free fermions. So it's a very nice and integrable point. Well, if Hx is equal to 0, it's really even more integrable point, because this is just spins up and down. Each spin is conserved. So it has as many integrals of motion as spins. In between, it's non-integrable. But now we can ask, suppose we want to reach integrable point. Because in integrable points are easy for experiments or for initializing ground states, which direction we should choose. So what's the, in some sense, most adiabatic direction? And as I was already telling you that the term which determines all non-adiabatic transition is a gauge potential. So what defines least adiabatic direction is, again, this geodesic, or the line where my gauge potential has a minimum. So let's try to see what we can get with this. And well, we are trying this variational approach, and now it's fully general, so it's Shou is doing numerics. So we are trying to solve this minimization problem, and we take ansatz for A, for Hx, and same for Hz, as we have single spin term, two spin terms, and the sigma could be arbitrary, x, y, z, x, y, z. So we basically do operator expansion. So it's variational principle. So we take most general operator, where we allow only strings of Pauli matrices up to length L. If we cover all system size, we will get exact, but it's very unstable and so on. And then what we want to do, we want to evolve eigenstates with this local gauge potential. And we know that if local gauge potential is good, then we almost get exact eigenstates. If it's bad, we will do a bad job. So, and of course, we want to find good directions where this is rapidly convergent expansion. And then this is just numerical results which show how interesting results can be. So this is a particular point where there is nothing particularly small. So h is 0.3, hx roughly 0.3 times sine of some angle, and so some generic point. And then we can ask how norm of this gauge potential increases with variational ansatz. So if it's local, it shouldn't increase at all. It should stay constant. If it's non-local, it should get bigger, 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 and bigger, so which tells me that it's harder and harder and harder to be adiabatic. And then, well, these gauge potentials form vector space. We can find good direction and bad direction. And it turns out that good direction is related to just dilations of magnetic field. So good, if this is my point, this is, say, HZ, this is HX. No, I think it was, yeah, I forgot how it was. Anyway, so good direction will be this direction along diagonal, and bad direction will be rotation. So what we see is that if you try to rotate magnetic field, then you are extremely non-adiabatic. You excite a lot. But if you try to slowly change amplitude of magnetic field parallel to itself, you're extremely adiabatic. So you just see the difference between two lines. It's huge. So this is norm of gauge potentials that increase ansatz. So for bad direction, it rapidly increases and becomes huge. Means I have many, many, many terms. For good direction, it almost stays flat.
This is kind of clear. If you rotate the field, you excite Goldstones.
Oh, there is no continuous symmetry, right? This is HZ, so there is no Goldstone modes.
Well, something similar to that. Yeah, no exact symmetry, of course.
Maybe. I don't. I'm sure there should be a simple explanation, but the fact that it's really parallel, you can imagine it's a combination of rotation and translation, or squeezing. But it's really this. Okay, so we found a good direction. Now we can say, okay, can we do something interesting with them? So in particular, we can try to find approximate eigenstates. Or if we're experimentalist, we can say once we know the good direction, it's the best direction for adiabatic preparation. Because if I evolve slowly, if I do it along bad direction, I'll still excite a lot. If I do it along good direction, I excite a little. So in some sense, it's like finding good directions for minimal dissipation in the parameter space.
Direction always leads you to a single point, 0, 0, right?
That's interesting, and we don't understand why. And it's highly degenerate, and I'll come to that. So this... Why?
Something integrable but not 0, 0. You cannot use this good direction.
Yeah, but what you can do, you can, if you want, you can go along good direction like this and then like this. So you can still, right? You can. So it's like if you want to go from this point to this point, yeah, it could be the optimal strategy. Could be like this. This we didn't study it, but it's kind of highly possible.
Problems.
Yeah, you might have problems here. No, you're right. So when you go along good direction, so the problem is that this is highly degenerate. So which state you are using as initial state, and we don't know. I'll show you some results. So we don't know good answer. So it's true if you start from a highly degenerate manifold, you really have to think what's the initial state you're starting from. But in any case, this initial state could be some superposition of up and down. It could be up-down state, I'll show some of your results, or could be like another domain wall state, or could be some superposition of those. So anyway, so this is work in progress. It's a very good question, but I don't have a very good answer. Anyway, so we can also do the same trick to integrals of motion, and then find approximate local integrals of motion. And I would say just existence of a good direction, right? Oh, sorry, it should be A. I apologize. I evolve with gauge potential. Just existence of good direction is already interesting. Because if I have exact A here, then when I evolve with exact A, I adiabatically address my integrals of motion. It means I get exact conservation law. But exact A is non-local. I cannot really find it useful. But if there is a good direction along which I have local A, I evolve along this direction. I get almost conserved integrals of motion. Just the fact that they exist is already non-trivial. How to get them is, you're right, it's another interesting question. Anyway, so I'll show you some numerics, and I will be done. I'll look into energy variance as a figure of merit. So we start from an integrable eigenstate, from an eigenstate which we know. And then and actually, to avoid this problem, what Shaw was doing, he was starting from very, very small h with exact eigenstates at small h, and then there are no degeneracies. because otherwise there is indeed this technical problem. Anyway, so we start from this integrable eigenstates. We evolve along good direction using gauge potential as our Hamiltonian, local gauge potential. And then we see how big the energy variance is. If we follow exactly eigenstate, energy variance should be always 0, right? But if we do a mistake, this is a figure of merit. This is how big the mistake is. And this is just numerical results. Let's just look into top curves first. So this is for comparison, good direction and bad direction. Vertical axis is energy variance. Horizontal axis is magnitude of magnetic field. And different color codes is different size of variational ansatz. So quench and single site variational ansatz, they actually coincide because for rotations, indeed I introduced this Pauli matrix Y, but for dilations, in single level, I don't do anything. So it's the same. So single site variational ansatz is doing nothing. Anyway, so, and then if I do just a quench, of course, if my h is small, I start from integral point, my energy variance is still small because I don't change the state. But if I suddenly go to a large h, I will introduce a large energy variance. So I have excite the state. But now I evolve with two-site variational ansatz, and I do really great job. I go down by, say, 2 orders of magnitude. So if I go along bad directions vertically, the numbers are much, much bigger, and they decrease much slower. So, and I'll show some other examples. We get good order of magnitude. But then there is something else which is happening. So it's interesting. In this example, once I reach a size of variational ansatz 2, in some other variational ansatz 3, I essentially almost stop decreasing. So it actually kind of means that I reached my optimal locality. It's basically as much, I did as much as I could do with my local dressing. And everything else just decays due to diffusion or whatever, non-integrability and so on. I can probably still do a very marginal power law improvement, but it's basically impractical. So essentially from here I see that two-site variational ansatz is extremely efficient. I can prepare states with very small energy variance, and beyond that, it's useless. And here you can sort of see how different terms behave, and then this is different ansatz size. So you just see that, well, here it's a different color code, or it's in progress, I apologize. So this orange here corresponds to gray here. Anyway, it's size 2. Anyway, you just see this two-body variational ansatz is large, and then three-body is tiny. Everything else is tiny, unless h becomes very big. Anyway, so, and I guess the final slide, I want to show that, well, what if we start not from one eigenstate, but from two eigenstates, superposition of two eigenstates? In integrable case, it's easier. It's just some combination of up and down. And here it turns out, in this particular example, it's just really single up-down state. It's a combination of some two correct. Because of degeneracy, I cannot really say it's 1 or 2. Anyway, and then if I evolve along good direction as my gauge potential, actually what happens in this case, I approximately create superposition of two very narrow excited states. And because they are very narrow, I have to create Rabi oscillations between them. Right? Essentially, no, if I prepare two eigenstates, that's trivial. My wave function will be A1 times some state n plus A2 times state m. This evolves with energy n. This evolves with energy m. And of course, I'll get Rabi oscillations. But why I cannot do it in practice, like in complex systems? We never see Rabi oscillations in like complex big materials. Well, because I cannot prepare eigenstates. Just difficult. Well, but now, using these approximate gauge potentials, you can prepare extremely narrow superpositions of these eigenstates. You start from 2, one becomes extremely narrow thing with energy, small energy variance, and another extremely narrow. And then from the picture you see you must have these oscillations. And this is some numerical simulations which shows that we essentially evolve with gauge potential, and then we look into magnetization and keeps oscillating in time. This is preliminary, so it's finite size so far and so on. And maybe it's related to quantum scars, which are very popular. And Dima had many papers on this. But anyway, so I think I told you enough. There are lots of other potentially interesting applications we are kind of discussing or talking about and so on. But I'm sure you got tired of me already. So let me just give a summary of what I was telling you in this 2 days. So one thing which I think is interesting and really worth exploring is that this non-adiabatic response very generally is connected to geometry of states. So, and like people keep asking how it's related to electromagnetism, general relativity. I don't know. But what we learned, at least from the simple derivation, the normal Newtonian dynamics is kind of self-emerging from just derivative expansion. So the reason we get first and second derivatives is not just some magic, but just because it's a Taylor expansion. It just happens that first order derivatives comes with sort of Berry curvature. It requires broken time reversal symmetry, and second order derivative comes with even if we if you don't break time reversal symmetry. Third order derivative will appear again, but it will be like a smaller version of the first order derivative. And there are examples actually we know, like if you have a relativistic system, there is a friction proportional to triple derivative of velocity. So that's there, that's part of this formalism. But normally it's a subleading term. But if it's a leading term, it will appear. So you just see the whole Hamiltonian dynamics appears as a gradient expansion. Well, you might think that maybe everything else appears as a gradient expansion, because at the end, all these theories like electromagnetism, general relativity, and so on, they contain sufficiently many derivatives just to satisfy whatever physics to the leading order of approximation. It's a speculation so far, but if someone is willing to bet, I'm also willing to bet that this is true. It has to be the case. Then we used quantum language, but I wanted to highlight that there are, I mean, many things have classical limit. And even geometry has a classical limit if I put correct factors of h bar. It's like Berry curvature times h bar has a well-defined classical limit, and that's what appears in physical response. Then we see that actually all these forces in nature, then kind of emergent as leading non-adiabatic response, like normally generalized forces, pressure, whatever, right? They emerge from thermodynamic equilibrium. So mass emerges in the same way. And then geometry, it connects many different phenomena, which I mentioned. Some of them I mentioned. Bass renormalization, quantum speed limits, counter-adiabatic driving, integrability, and so on and so forth. Yeah, one thing, sorry, I forgot to mention, these diagonal directions are kind of very interesting. So if you are close to integrable points, diagonal directions become automatically almost parallel to integrable points. So in some sense, integrable lines. So in some sense, if you don't know whether your problem is integrable or not, and you are finding a good direction, if you really find a good direction, most likely it brings you parallel to some integrable line if it's there. Anyway, it's speculation. So I really want to thank you for bearing with me. Thank you.
Maybe some question arisen? I have a question still. Why D-Wave is not introducing counter-adiabatic protocol?
I think they're in discussions about this with.
So they do know about this approach?
About these two-spin things, I don't think they really know. About single spins, no, single spins they must know. Counter-adiabatic and open systems are not that developed, but I know that people like Ash Clerk, who actually study some versions of counter-adiabatic in dissipative systems, they are talking with D-Wave people.
Look, the thing about glossiness you mentioned about looks like a direct way to obtain this bloody quantum supremacy after all. Yeah?
So one has to look at. I know one paper from Innsbruck group, Innsbruck, but not Peter Zoller, but sorry, I forgot the names of people. Marcus, I forgot last name, yeah. So they used a very specific model, which actually in Peter Zoller group was developed, which is NP-hard. And this is essentially spins with non-local but disordered interactions. I think there are 4 spins, 2 spins. Anyway, it's an NP hard. And they applied they basically used exactly our variational procedure and applied single spin protocols. And they showed like huge increase in fidelity. And I asked them exactly the same questions you asked. So can we really apply this to sort of D-wave architecture? And they say they're thinking about that. I don't know if they're talking to these guys or not. But my guess that this is relatively new stuff, especially for interacting systems. For non-interacting, there are experiments now that we're doing. For interacting, it's really new. So I suspect that this will be implemented soon. At least I don't see conceptual difficulties because, like, here we see 2 spin terms. We actually now have another work in progress. 2 spin terms you can implement using Flocky. So one can ask, like, maybe D-wave doesn't have very good control of 2 spin interactions. Maybe they do, actually, don't really know details. But even if they don't, if you can shake your magnetic field along X and Z in the presence of static interaction, you can actually generate these terms. So it actually means you can realize these high fidelity gates. But of course, the question how the procedure converges. Like one thing we studied and didn't publish, can you really cross Anderson localization transition? Well, not Anderson, this Audrey-Ambrame model, whatever. In 1D, there is transition from localized to delocalized states. And it turns out with local gauge potential, you can really well reach the boundary from one phase and from another phase, but you cannot cross the boundary because things become non-local.
Someone tried to implement this at least in numerical simulation?
For D-wave?
Well, not for D-wave, but just take, I don't know, Sherrington-Kirkpatrick model and...
No. It's, I don't... this Innsbruck group was the first one I'm aware of which tried this variational approach. Perturbatively, people tried, because perturbatively, people derive approximate Schrieffer-Wolff transformation. You can show that if you perturbatively try to solve this equation for the gauge potential, get identical results. And there were actually very interesting works about sort of generalized Gibbs ensembles in weakly non-integrable systems. I think Fabian Essler was one of those. So they did a quench. So you do a quench, you turn on some interaction, and then you ask what sort of the steady state. And first guess it will be, I guess you'll hear about this later, I assume. Steady state will be generalized Gibbs ensemble. But it turns out that actually the conserved particles are not that conserved anymore because you turn on interaction. And what Essler and company did, they dressed this conserved particle to the leading order interaction. It turns out that perturbation theory works to the second order, then it becomes singular. They dressed, and then they constructed generalized Gibbs ensemble with these dressed quasi-particles, and it worked extremely well. And this dressing, in this case, is equivalent to this 2-body essential variational or whatever perturbative ansatz for the gauge potential. Because when you do Schrieffer-Wolff transformation, you actually try to find this unitary. It's usually called S, and I think Eugene was using it. It's e power S times some I times e to the minus S should compute with H. You're trying to do it. But this S is nothing but time pass-ordered integral of the gauge potential. So you can sort of use Magnus expansion. So getting expansion for S is actually much more difficult than expansion for A. But it's the same object, essentially. So it's not that it's not known, but it's not probably explored well in this language. And this is only perturbative. Variational is much more powerful. I'm talking about regimes where changes are huge. So H goes from 0 to 2 when J is 1. So it's more powerful than Schrieffer-Wolff.